Okay, so let's read the question. A force F is applied at D. That's the force. Assuming that the material is ductile and the critical point of failure is A, compute the value of F, assuming maximum shear stress theory, distortion energy theory, and yield strength is 81 kpsi. Okay, now in this case, you're told that point A is the critical point, but for a problem like this, and you're an engineer in the field, you will not be told which point is critical. So you need to basically go around and plotting the stress, maximum shear stress or the distortion energy stress, which is the one Mrs. stress at every point. And then you'll find the point where you have the maximum stress and use that to design. So a software like ANSYS will do this for you. It'll give you the stress for different parts, and you'll just be able to tell which part has the highest stress. And then based on that stress, maybe you'll use a factor of safety to design it. So then you can vary maybe the diameter of different parts or the length of the lever and so on, and figure out how the stress changes. That's maybe something you did in senior design. Okay, so let's solve this. We need to find clearly the stress at point A. We need to compute the shear stress at A, and we need to compute the von Mises stress, which is associated with distortion energy at A. So in order to do that, we need to first compute the loads at A. Unless we do the loads, we can't find the stress. Let's look at what sort of stress element we need to draw at A. Once we know the stress element, we know the stresses. From that, we can identify what loads come there, and then we can connect them with whatever is asked. So at A, if you take a point, okay, and then blow it up, this is our stress element. Okay, now this stress element here in top, you can see that the x-axis is this way. So this is, I'm viewing this element from the top, right? I'm seeing it from the top. So when I see it from the top, this axis is the x-axis. So I drew the x-axis, sigma x. This axis, the normal axis, is sigma z. And then clearly the shear stress here would be tau zx. Yeah, so what's asked? We asked to compute F using A MSS, B DE, and we're given the yield strength as 81 kpsi. Okay, so one way of doing this is what we'll do. Steps. One is, first we'll compute sigma x, sigma z, tau zx as a function of F, right? F, the stresses are because of F. The second step is compute tau max, which is the maximum shear stress, and sigma prime, which is the von Mises stress. This is the stress associated with distortion energy. And then third, we'll equate tau max is Sy divided by 2. This is by the MSS theory, right? MSS theory, this is the failure criterion. And for the von Mises, sigma prime equals Sy. This is for DE. And this will help us solve for F. So we just do this 3 steps, and and we are done. Okay, so this part requires perhaps FBD, SFD, bending moment diagram, strength of materials. Okay, this is typically a Mohr circle problem. And this is a failure theory problem. So now you can see that how what you learned in probably statics class, strength of material class, this too ties with what we're going to do in design. Okay, we've also done this in the previous classes, so hopefully that was good review for you. Okay, so let's get started. So we have a force F, and that force is going to cause a stress at A. We need to identify what sort of stresses are created at A due to F. Okay, what have we learned so far? We've learned bending moment, we've learned about torques, we've learned about shear forces, anything else? And of course, uniaxial forces, so 4 of them. I'm just going to redraw that and then we can start solving it. Let's do part 1. This is going to be 1, 2, 3. That's how we'll go about doing it. 1, compute sigma x, sigma z, tau zx terms of F. Here we are going to also ignore any stress concentration, because you see that at A there's actually change in cross section. You see the change in cross section. There's a 1/8 inch fillet. So if it is a real problem, you'll have to consider the stress concentration. But we're going to ignore the stress concentration here, unless you're asked. You can ignore it. So ignoring the stress concentration, we have this point A. And then there's a lever. Okay, this doesn't have to be very accurate. There's a force. Might help if you draw the axis. So I think this axis is X. X, Z, Y. Okay, let's draw some lengths. So this point D is at a distance of 15 inch from this line. And then this point is, see, 12 plus 2 plus, 12 plus 2, 14 inches from A. I'm just going to draw that. This distance is a different color. 14 inch. And then this distance, 15 inch. Okay, and then also I drew the plane stress element here. So the top view, sigma x, sigma z, tau zx. Okay, so probably the easiest one is to see what the effect of the force F will lead to a torque, right? And the torque is clearly due to this force times 15. It's going to cause a torque in this fashion. So that torque will clearly cause the point A to have a shear stress tau zx. So we know that tau zx is going to be a torque times the diameter at A divided by the polar moment inertia at A. So this torque here is going to be F times 15 or 15 times F. The diameter at A is given, it is I think it's 1/2 inch. Oh, sorry, this is 1/2. Is it 1/2? Okay. So 3 divided by 2. Oh, but wait, oh, this is 1 inch. Oh, top. Yeah. Mm. Yeah, this is how I assumed it. Yeah, let's assume A to be here. It just doesn't matter. It's just a matter of calculation. Let's just assume that A to be, nothing is given, right? No. Yeah. I guess O, well, then O would be the point. Well, let's assume that A is on the 1 inch. Okay, yeah. Let's make our life easy in calculation. So assume that this is on the D equals 1, small d, 1 inch. Doesn't change much. So this is 1 inch divided by pi. It's d cubed divided, d raised to 4 divided by 32. So 1 raised to 4. You know what? Let me write the formula down here. dA pi dA raised to 4. So 15 dA cube divided by, sorry. This should be dA divided by 2, my bad. Right, this is with the radius. So it's 16 dA cube divided by pi. This will be one part. And the other part is 15F. Okay, when we just have to put dA equals 1 inch. So everything except F is known. So this comes out to be 76.4 F. Okay, so we've accounted for that. Now let's move on to try to understand what else could be produced due to F. So due to F, there would be a bending moment. So there is a torque, but then it also produces a bending moment like this. So this torque, better way to show the torque would be with an axis. This is the torque, and the torque is acting about the x-axis. For the bending moment, there will be, this is just, there's a bending moment in this plane. This is the this is the xy plane. So there's a bending moment like this. This is the z-axis, sorry, the z-axis. This is the moment M. It's actually mz. If you like, you can call this actually tau tx, right? It's torque about x. So the way you think of torques is that if you take your right hand, you point your thumb in the direction of x, then your curled fingers will give you the direction of the torque. So again, take your right hand, point your thumb towards the positive x-axis, and your curled fingers gives you tx. So if you like, you can call this tx. Okay, so there's a bending moment m, z as shown. Same trick applies. You take your thumb, point it in the direction of z, and your curled fingers gives you direction of mz. Here, mz is in the other direction. It's clockwise, so it's negative really. Here it doesn't really matter because yeah, it doesn't really it doesn't matter. Well, mz, the way I've shown it, right? This force will clearly cause mz to be this direction. If you see it from here, you see that it actually causes it to bend this way. What it does is it causes the point A to be under tension or compression. Tension, right? So it's tension, so it's positive. So even though direction is negative, it's actually tension. So sigma, and it's going to be sigma x or sigma z. Will it be sigma x or sigma z? Sigma x, right? So it's going to be, remember, this is the top view. This is the top view. What I've shown here is the top view. So it's sigma x is mz. We need to refresh ourselves on how do you compute the stress due to a moment m. It's basically m y divided by I, right? This is pure bending if you go back. Y is the diameter divided by 2. It's the distance from the neutral axis. And the moment of inertia is pi dA raised to 4 divided by 64. So the moment mz is what? It's F times 14, right? So 14 F dA cube divided by, let's do it this way. So we write this as 14F, and I'm going to just move things around so it looks very similar to this expression. So first I have 32 dA cube divided by pi. This is just the contribution due to the second part, not due to mz. And the mz part is 14F. Okay, now I know that this is 1 inch. And so I can solve for sigma z. Sorry, sigma x, my bad. Sigma x is 142.6 F. So this is what I need, and this is the other thing I need. Okay, is there going to be a sigma z or not? Sigma z is this way. Is there any stress due to F which will cause a sigma z? So remember, there are only 4 things we studied: torsion, bending, shear, and uniaxial stress. Clearly, F is not, it's not going to be uniaxial. What about shear stress? Do you think there'll be a shear stress at A due to F? Okay, why not? Okay. So this is clearly not in the direction of this plane element. So there's nothing to worry about. But let's say that I did introduce a force this way. Let's say I put a force here, F1. Do you think there'll be a shear stress at A if there was a force in the direction of Z? Okay, this is a simple way in which students make a mistake. Even though the shear stress, it's force at Z, the shear stress at A should be due to the shear force is 0. Because if you remember, when there's a shear force, the force looks something like this. The maximum occurs at the middle point, and the force shear stress is 0 at the edges. So even though there's a force, the point A is on the top. It's not in the middle. So there will be no reason why there would be a shear force, even if there was a force in the Z direction like this. The shear stress at A would be 0 because it is on the surface. It is not in the middle. If that point A was in the middle, then the shear force, the shear stress would be non-zero because the shear stress is maximum. So I find that this is a very common way when students make a mistake in the homework, in the exams. It's interesting, if I switch the point A to be at the middle, all these forces, all these stresses are 0. This is 0, and this is 0, because remember, the torsional stress is 0 in the middle. The normal stress is 0 in the neutral axis. So now it just becomes, actually, there's no stress in the middle in this particular case. Okay, so we've got sigma x and tau zx. Where were we? We were solving for. We're going about this. We've done one, which is, by the way, the hardest part. Let's do the Mohr circle. You can do the Mohr circle, or you can just compute it using the transformation formulas. Let's compute the maximum shear stress, tau max and sigma prime. For that, we need to compute. So stress step 2. Compute tau max, which is MSS, or sigma prime, which is 1 misses due to DE. So for tau max, we need sigma 1 minus sigma 3 divided by 2. And for sigma prime, I think it is if I remember right, it is sigma x square plus sigma z square minus sigma z sigma x plus 3 tau zx square. I'll just convert from z to, it was, the formula is for xy, but I just changed it to zx. Okay, so sigma 1 is the maximum stress. We can actually write the formula for sigma 1 as sigma x plus sigma z divided by 2. If you remember, it's plus or minus sigma x minus sigma z square plus tau x z square. Actually, let me write this as sigma a, sigma b. Okay. Sigma x is 142.6. Sigma z is 0, plus or minus 142.6 f divided by 2 square plus tau xz is 76.4. Maybe 1.5 plus or minus 5f. Okay, so sigma a, just pick one of those two signs. And let's say sigma a is 71.3 plus 104.5. It's 175.8 times f. Sigma b is with the negative sign, it will be minus 33.2 F, and then sigma C, which is always there, like a third stress, which is 0. So clearly, we need to rearrange them in the descending order. So sigma A is greater than sigma C is greater than sigma B. Right? So sigma 1 is sigma A, sigma 3 is sigma B. So sigma 1 is 175.8 F, sigma 3 is minus 33.2 F, and from this, tau max is 104.5. Is that right? Yeah, it'll be minus of minus, so it'll be right. I'll write it down. 175.8 F minus 33.2 F divided by 2. And 4.5. Sigma prime, luckily there's a formula which we can use the formula. I think I made a mistake here. This should be square. Sigma prime is sigma x square, sigma z square minus sigma z sigma x plus 3 times tau zx square. Okay, so clearly the stress sigma z is 0, so this is 0. Sigma z times sigma x will be 0 because sigma z is 0. And so we are left with sigma x and tau zx. So sigma x was computed in step number 1 right here. Sigma x was 142.6 and sigma tau zx was 76.4. Okay, so I'm going to write that down. 142.6 times f square plus 3 times 76.4 square, and this works out to be 194.5. Okay, so we have the von Mises stress, and earlier we had computed the maximum shear stress. So we are all set to do the final step to compute capital F. So this is step number, let's see, what did I write? 3, but was it? Okay, 3. Perfect. 3. Compute F. Okay, so for that, what we do is we use the criterion that for MSS, the criterion is that tau max should be equal to SY divided by 2. So tau max was 104.5 times F. The yield strength was given to us is 81 kpsi, so 81 times 10 raised to 3 divided by 2, and we can easily solve for F. It's so F, let's say F from MSS is 388 pound force, and then if you use DE, the criteria is sigma prime is equal to SY. So sigma prime is 194.5 times F. SY is 81 kpsi, so convert to psi. You can solve for F using DE. That comes out to be 416 lbf. So that basically solves the problem. But let's see something which came out from this calculation. So the loading is the same for both stress theories. We computed the net force. We found that the force due to dE is greater than force due to ms. That is what it's saying, is that you can apply a lot more force for distortion energy than you can with maximum shear stress theory. In other words, what maximum shear stress theory is doing, it's being more conservative. It's saying that don't go beyond 388, but D is telling you go up to 416, which means that with D, if the material behaved like D, then you would be able to apply more loads. So it would be less conservative. So this means that MSS is more is more conservative. Let's say this means MSS is more conservative than DE.